Hello, I am Teodora, and today I'll try to summarize a very beautiful field in machine learning in 45 minutes. So brace yourselves, put on your seatbelts, and let's go. So until now, we have so many advancements done by many people in what regards neural network, right? We know that MLPs are universal approximators, then depending on geometric priors, CNN advancements were made and GNN advancements were made, and language models are now a thing because of that as well. And until 2014, let's say that in what regards the state of the art, people were kind of convinced that we have good discriminators, so we should also have good generators of data, right? But what is a discriminator? So a discriminator is a model that is able to differentiate between different classes of data, right? And then a generative model is a model that, given the data samples, is able to say, generate other data samples, right? We use picture generation models to generate pictures given text and all of that, and these samples have never been seen before, but that's what a generative model does. So is generating that easy? Like, do we put magic into a black box and then we get our images with cats coming out of it? It's not actually. So let's talk about what it means to generate. So when we try to generate, what we have is usually some data points, right, coming from some underlying distribution P of x. And what we try to learn is a f function that will generate other x points. Ideally, we never seen these x points before. Other cases, when we are trying to generate, we might put also a label of the thing that we are trying to generate. For example, we have a model that is learning to generate cats and dogs, and we would like to make it generate only cats, so then the input of this function would be also the label cat. Why do you think this is quite cool? Like, does anybody have some intuition to why this is a bit cool? Raise your hand if you have some intuition.
Because we can sample this.
Yes, so generative models kind of have discriminating power, right? They're able to understand what is a cat and dog and also generate them. So they're a bit smarter than discriminators. Okay, yeah. Okay, let's imagine this, picture this. We are in 2014 and we try to make this generative model with the state-of-the-art people back then. And we have natural questions like, what is F? Is F deterministic? Is F a neural network? What is the input of this F thing? You know, what can we do? So from what we saw now, I think it is fair to assume that F is a neural network. But then, if F is a neural network, given the same input each time, it will spit out the same output, right? So we really have to think what is the input of this neural network in order to be able to spit out whatever probability distribution that we want it to be. So, yeah, if let's say Z is the input of our neural network and X is the distribution that we're trying to learn, I'm asking myself, can Z be a natural random variable, for example? That is like 1, 2, 3, 4, because I know how to generate this. I have my PyTorch library. So can it be that? Yes, no? Who is for yes? Raise up hand. Who is for no? No? Okay. So, are you ready to find out? It can't be, because X is ideally, continuous, then neural networks are kind of continuous function themselves. So, if Z is kind of like a deterministic points in space thing, I can't generate a continuous thing at the other end. So Z needs to come from a continuous type of distribution. Can Z be a normal distribution? Yes, it can. And we can also generate numbers from normal distributions. So this is very nice. But, however, it's not that trivial to actually generate numbers from a normal distribution. And In the lab today, this is a question that you will get to explore if you want to. Okay, so we have some intuition to what we are about to design. We need this neural network. The input will be Gaussian, right? And the output will be what we want to learn. Let's go. Let's find out how people did this. So in 2014, two architectures were invented. One of them was variation autoencoders, which I will show today, and the other one was GAN. With variation autoencoder, what happens, and it's very confusing, I'm sorry for this, but you will see this formula so many times that you need to have courage when looking at it. So we have an encoder. This encoder encodes our images to some sort of lower space. This is usually called, in state-of-the-art, latent space. And then we have a decoder that tries to decode the latent space to the original picture. And in the loss, we have the reconstruction error. So how well is the encoder encoded thing decoded, reconstructing the image that we encoded in the first place? So for example, it can be like MSE between X and X hat. This is what reconstruction error does. Then we have a KL divergence, which is basically forcing our latent space to look like a Gaussian. Now, before variation autoencoders, there were autoencoders that didn't have that ugly KL term. Does anybody have some intuition why that KL term is needed in the first place? Like, yes? No? Okay. So actually, you know, if we don't have the second term, we don't know how our latent space looks like, so how are we going to generate more samples? Like if I want to generate using the decoder, what am I putting inside the decoder? Because I don't know how P of Z looks like. So this is why we need this KL divergence to force our P of Z to look like a Gaussian. So this is a kind of a dual optimization type of thing. While it trains the model to reconstruct the images well, it also trains the latent space to look like something I'm comfortable sampling from. So later on, I can sample from a Gaussian, put it in my decoder, and generate new data. But, you know, as, let's say, for GAN, which I won't explain today, but it's a very beautiful idea because we train a generator without the generator ever seeing the data. Had multiple issues like mode failure. This means that if it was comfortable for the model not to learn the digit 4 from the MNIST data set, then it would just not learn it. And, you know, I mean, people were quite happy with the quality of pictures, but also quite unhappy that they didn't reach that peak of generation. So let's see what happens after 2004. So as we can see, in 2014, VAE and GANs appear. Until 2020, there were many GAN plus something type of papers that added some new functionality on GAN, and then GAN worked better. At the same time, in 2017, beta VAE came on. Beta VAE is basically just adding some weight to this KL divergence thing, such that this dual optimization type of thing was controllable instead of randomly telling a network, yeah, do this for me. Okay, and in 2020, something really exciting happened. So hierarchical VAE and denoising diffusion models, probabilistic models, appeared. So these three models have something at their core in common, and what they have in common is that they use dynamics when generating data. So let's understand, you know, and also, why is exciting? It's exciting because it gave birth to a capability of generating high definition videos and all type of stuff, right? And proteins and so on. So behind the scene with diffusion models and flow matching, how many of you have heard about diffusion models and flow matching? Raise hand. Okay, so not so many people. These are generative models. behind the scenes for them, we kind of try to learn dynamics between a Gaussian and the distribution that we are interested in. And the dynamics are either ordinary, either stochastic. What are ordinary differential equations and stochastic differential equations? So in this world, we have many dynamics type. Deterministic are very nice because we can always ask where will an object be after t time. Unfortunately, with stochastic dynamics, we can't do this anymore. The questions we can ask are usually like, with what probability will an object end up in an area of interest, right? And now I will try to give more intuition to both of them. So with deterministic dynamics, what is happening basically is that I have a landscape and let's say some objects that interact with my landscape, and I can ask where will the purple ball, for example, be after t time, given its position. And what I can do is kind of query the environment for it to tell me where it will be in some time t. Given the size of the steps, for example, if I take big steps, this approximation might go very wrong. And if I take infinitely many steps, then what happens is that I get ODE and I get to integrate over it and I get no error and I know where my object will end up. Beginning of stochastic dynamics. Okay, picture this. You're in 1827, you're a biologist and you watch through your microscope and at pollen particles in water and you see that they, why do they jiggle? Why do they move a bit? Does anybody know why pollen particles move in water actually? Why do they jiggle? No? What is there in water to interact with? So you have this particle, right, that you put in water and then it starts moving around. What could it interact with? Yeah, with water molecules. Wow, you could have been Einstein, Too bad you were born, 100 years later. But yeah, so basically Einstein for his PhD thesis said, so we have this pollen particle and it's hidden from various directions by water molecules and I can predict how far it will get and the distribution of how far it can get is actually a Gaussian and yeah, after that we all know what he did, but this is what he did for his PhD and to this day I'm wondering what am I doing with my life because okay, but as we all know, Einstein wasn't a very good mathematician. Like he was always employing other people to do his math. So of course there had to be another guy who actually did the formal work. Paul Langevin knew what the ODE looked like. So he asked the obvious question: how can I formalize this to obtain a stochastic differential equation? What would that mean? How would it look like? What would it mean to integrate over it? What is the solution of it, right? And he said, it looks like this. Job done. I'm joking. So basically in here, what is happening is that this looks ugly. VT is kind of like winner process type of thing. I'm not going to get into that. But we can look at the solution of it, which is a bit more human friendly. So the solution of this stochastic differential equation, so the position of xt, right, is x0, that is the initial position, and then a Gaussian times some delta t squared thing. So it's actually a Gaussian with mean x0 and standard deviation delta t. Does that make sense? Kind of? No? Yes? It makes sense? No? We know that when you multiply a thing by a Gaussian, that thing, if the mean is 0, goes to the standard deviation, right? Squared. So that's why I'm saying that the solution is actually a Gaussian with mean 0 and standard deviation squared. And in our case, the standard deviation is 1 and the coefficient is delta t squared. And why is there a delta t squared? You can explore for the lab. I think is actually quite interesting. So if we look at how we integrate over finite step for ODE, we always get that delta t small step, but in the case of SDE, we also get for the drift delta t, but for the kind of noisy part of the describing the random movement is the square delta t. You can try to find out why that is. I think it's quite nice. I don't know. Okay, so let's get some intuition into how ODEs and SDEs differentiate between each other. So, for example, in this case, I'm presenting two different ODEs with the same noise added, which is 1 times dW t, which for now, if you just think as adding random noise is good enough. So what we notice is that in the case of ODE, because d of xt equal xt dt is just exponential, right? The solution of it is an exponential, so the curve we'll draw is kind of looking like an exponential. Then I'm looking at 1 minus xt, it will look like a logarithm type of function. When I add noise to this kind of dynamics, what I can notice, and I think it's quite cool to see, is that even though I add the same noise to them, my drift is making the same noise. So even though I add the same noise, the drift is making the solution look up differently. So we can see in the one below, the noise gap is kind of smaller than the one above, even though the same noise quantity is added, right? So I think this is quite nice, and it's quite good to know that if you add noise to an ODE, it's not super obvious what happens with it, basically. And this is just to show what if we add other type of noise, right? So the first two we just saw, and the third one it's new. In this case, I'm adding t times 1 minus t. This is just saying that the noise that I'm adding will be very small at source and target, because when t is 0, that coefficient will be 0, and when t is 1, that coefficient will be 0. And what I can notice is that for the same drift, again, the end distribution that I'm ending up at time 1 with, in the case in which the drift is kind of more negative, is smaller than in the case in which I have a kind of an exponential looking like function. So it's okay. Just so what you need to remember from this is that don't make assumptions on how noise interact with drift and how drift interact with noise. They're very codependent on each other. Okay, why are stochastic dynamics quite cool? So let's say that I am running my cute little experiments with the balls, right, on this beautiful canvas, and if I run it as an ODE, so I assume that my environment has no noise, the gray ball or the white ball will always end up on the left-hand side, right? But life is not like that. We always have noise in the environment. So imagine that when the little ball gets in the saddle point and is kind of trying to decide where to go, a little kid comes to my table and shakes it very hard, I would say half of the times he would end up in the other minima, right? So again, stochastic dynamics is kind of cool, like it allows you to explore your environment better. Okay, now that we kind of have some intuition to what this means, and that we kind of have some intuition on learning a vector field or stochastic dynamics over it, and we kind of know how to integrate over these dynamics, it would be nice to also learn how to code these models. So there are two big models that kind of, I don't know, if you want to write a paper in generative modeling, you're aware of these two and you think in terms of these two. There are diffusion models. So diffusion models have this kind of stochastic differential equation background, right? As we can see, we have some data samples, and in here I trained both a diffusion model and a flow matching model on the same data. And what we can see is that with the diffusion model, it's not really obvious what point will go where and when. With deterministic flow matching, however, we can almost see how our Gaussian is split into 3 and then it converges to the data samples that we are interested in. Because stochastic diffusion models are quite involved, and there is a lot of theory to them, and the first paper that appeared with them is really complicated and scary to understand, I will try to give some intuition for the flow matching model. Even though, funnily enough, you know, the denoising diffusion model appeared in 2020. It is 10 times more complicated than the deterministic version of itself, which appeared in 2022. Okay, so for flow matching, what we want to do, we have a distribution P0, which we know how to sample from because it's our beloved Gaussian. We have a distribution P1, which we don't know, but we have samples from it. So then flow matching says, okay, I would like to know how my distribution would look at time t, given that I make the assumptions that the paths between my input and target points are straight. So then it says, actually, xt is just the straight interpolator between the two. Does anybody know how a straight interpolator looks like? No. Are you ready? Wow. It's just, you take your x0 point and then your x1 point, right? And xt is just a point on the line from time 0 to time 1. I mean, given some time t in 0, 1, it's just is everybody comfortable with this? Okay, good. Okay, then people are like, okay, I kind of know how xt look like, so how can I define the vector field of this? And you know, like, vector field is kind of the derivative of xt depending on t. Does anybody know what that is? People are, yeah. Are you ready? Whoa! It's so hard. Minus x0, because you know x0 has the coefficient minus t, so when you differentiate with t, that becomes -1, and for the t, when you differentiate with respect to t, that becomes 1. So, wow, this is the vector field we are trying to learn. And now for the loss function, we are trying to approximate this function, right? We have our model that wants to approximate this vector field, so it's just a neural network that tries to approximate -x0 plus x1. The way I present it to you is quite unfair. So I fooled you a bit, right? Because the way we sample x0 and x1 is actually independent. So even though I will sample an x0 and x1 at xt, there are infinitely many other pairs of x0 and x1 that go through that point. So this is why this function is hard to learn, and the way I present it to you is unfair. But I think it gives good intuition to when you read the paper, you feel more comfortable with what you see rather than be very scared and confused. And now, this beautiful paper, so this is from Yang Song Score Matching Diffusion Models paper. They say, oh wow, I have some SD that if I run forwardly, I will arrive to a Gaussian, and then theory tells me that there exists a reverse SD that can take us from the Gaussian to the data. And in this very beautiful formula, I have gradient of x of log pt of x. I'm so happy I understand what that is. And it is I mean, log x gradient of log pt of x, which is called a score function, behind the scenes, the intuitions of it are quite beautiful. So I do recommend reading the paper, but don't be afraid of it. What it's saying is basically, okay, when I go forward and I add noise to a drift, to some points, my noise will interact in some way with these points, right? So when I go backward, it's not super obvious how my points interacted with the noise I added. And that gap is given by this score. Now, if you do read the paper, they will say, oh, this thing is intractable. And then you basically get into the insights of the paper and learn how to approximate it by conditioning it on the x0. And life is beautiful. You still need to revert it and then integrate over the reverted SD and then cross your fingers that you don't have to debug for 10 hours. But I swear to you it works, and it's a very nice method. Okay, so the way I presented to you kind of these generative models is that behind the scenes they're the same. So there is this amazing paper that actually say how they are the same. And you can actually learn a score matching model in a flow matching way and then use an ODE to integrate it. Okay, so what I show in this picture is that I have two processes, right? One is an ODE and one is an SDE. And the ODE learns how to transform from two moons to a chess table type of situation, and then the SDE does the same thing. This paper says for each ODE, there exists an SDE that will have the same marginals as the ODE. So if we look at how the distributions look in time, they look the same, although the processes are different. So if I start with a particle and kind of run the ODE to see where it'll end up, in the case of ODE I know, in the case of SDE it could end up kind of anywhere, but the marginals are the same for both. And I think this paper came 2 years ago, and it kind of brought flow matching people together with diffusion model people to have a common denominator and fight against generating data together. So if you are interested in how this works, I really recommend this paper, and I think you should check it out. Another cool application is geometric flow models. So if we do run our model on running how to learn to go from the red to the blue points, I don't know if you can see that they have different colors. I'm sorry for this. So on the top they're red, and on the blue on the bottom they're blue. If we kind of learn in the flow matching way, what we'll notice is that the lines or the vector field that we learn is kind of straight and is not really following the topology of the sphere. And some people like to run dynamics on surfaces, right? And this is what geometric flow-based models do, and you can read the paper of my colleague. It was published at NeoRIPS in 2014. He proposes a solution for this. But basically, the solution to kind of this problem is that instead of assuming that our interpolator is straight, which we have done with great happiness before, we want to assume it's straight plus something. And this something thing can be a manifold, metric, like anything that can tell us how our object looks in space, a kind of a correction, right? Another cool application of it is optimal transport. So this is not an optimal transport friendly example, but I think it's a friendly example in general. So I think we all solved this problem, but then some weird, I am one of them, weird people were like, but what is the minimum steps I can solve this problem? So this is kind of optimal transport question, right? Like, okay, I know you can solve this problem, but what is the minimum steps that you can solve this problem in? So this is, for example, in flow matching or in generative models, is the problem of moving mass from one side to the other. And yeah, how to do that in an optimal way by minimizing a cost. Minimizing a cost could be cost of transport on a manifold. I don't know. You define it. And people have done it. Alex Tong has a paper. I also recommend reading this paper. He's using a really nice method to enforce this kind of optimal flow matching type of vector field learning. So if we look at these two figures, what we see is that in the case of flow matching, the paths kind of bend. I am sure that a path that bends is longer than the straight path. Like, I don't need the cost function to kind of realize this. In the OT case, what they wanted to was to straighten this path at maximum. So the solution they propose is at a batch level, try to enforce this optimal transport thing by using something you can find out reading the paper. And also, if you do, or if I sold stochastic kind of score-based generative models to you via the easier version of it, which is the ordinary one, I really recommend this book. It's very friendly. It starts from the basics. Like if you know some OD integration methods, you will be able to read it. And I really recommend this paper. I always go back to it. In the appendix, it has so much content and it answers to so many questions that you have as somebody that comes new into this field. And yeah, I mean, just have a chat with your favorite AI agent about it and he'll explain things. But yeah. That's it, thank you. Any questions?
Thank you for the lecture. One question about the last slide, where you were presenting a cross-interval method and OT cross-interval method. So maybe I just didn't get the idea. Why does they work in such a different way?
This one?
Yes.
Okay. So, do you remember when I told you that I kind of cheated on you with saying this, just straight interpolator, because there are infinitely many x0 and x1s that kind of pass through this point.
Yeah.
What this paper does is at a batch level, it kind of ensures the pairings between x0 and x1 are more nice than just random. And it uses Synchorn algorithm to do this. So it uses an algorithm to kind of make sure that the pairings make sense in space, right? Otherwise, they would be just random. But with this algorithm, they behave nicely at the batch level. And doing this at the batch level, of course, it doesn't happen globally. This is not the solution to OT, right?
Yes.
It is not. It's just a nice finding that is not that expensive.
Yeah, got it. Thank you.